Okay. Well, great. Thank you for having me. I thought this has turned into an interesting talk as I was preparing um, for this because I think most of the stuff that I presented previously, well, I wouldn't say most of it, but a lot of it related to this topic was a little bit theoretical. We're now 2 years into a project that we call the 40 Farm. And this project is kind of taking a lot of these theoretical ideas and testing them with what we're doing. And we're trying to, um, uh, we have a demonstration farm. 4D stands for Digital and Data Driven Demonstration Farm. So we have a farm that's about 90 acres, and it allows us to perform data collection and analysis on the information we're collecting. Um, I'm going to show a little bit of the data collection that we're performing now. We've started a dashboard on our website to continuously update information that we're collecting. It's still a little bit of a work in progress, but I think you'll get a good idea when I show you that. Um, some of the practices or some of the projects that we're implementing on the farm that I'm going to talk about are basically how can we collect data, turn that data into useful information, and then take action on that. And this past year may have been the first. We're just ending the second year of the 4 years of this project, so we're just now kind of getting enough information to um, create some of the analysis that's needed to generate that prediction or simulation that we can use to um, take action take action on the information. Sorry, I got something in my throat. So the data that I'm going to talk about primarily is on irrigation scheduling. How do we forecast the need for irrigation before stress is apparent in our crops? Plant growth regulation. So again, it's forecasting the need for plant growth regulation before um, the energy is not properly utilized by the plant. So plant growth regulators help manage the growth of the plant and when it converts from, say, vegetative to fruit development. So all of these studies that I'm going to talk about today is with cotton, but there are plenty of crops that would utilize all these. It's just that's the data that we're collecting on our farm. And then yield estimation, which is how do we adjust inputs during the season, um, utilizing some of this information that we're getting. So the yield prediction will be adjusted as we collect information and adjust these things that we're uh, managing during the year. So if we avoid stress on the plant, how does that help improve our production at that point? And then and I'll talk a little bit about database evaluation, where we're testing out a few different databases to see which one is best for managing farm data and performing these analyses and then feedback to the farmer to make management decisions. So the project, as I mentioned, is the 4D Farm. It's about 90 acres total. It's about 40 acres under pivot. And when I say pivot, that's a method that we use to irrigate the crops. It's called a center pivot irrigation system. So it goes in a circle and sprinklers drop water on the plants as it goes around. The part that I'm going to just talk about today, as I mentioned, is the decision support management assistance that we're going to try to develop, where we collect the data and make management decisions based on that through analysis of that. I'm going to show our website that we have right now. and I'm going to show the dashboard, and I'll talk about the dashboard later. Wait just a second. Let's see. Okay. So you should see, this should be the front page of our website. It's just called 40 Farm, but we've been updating these tabs over the last year, particularly the education, extension, research sites, updates and dashboards. So Data Explorer is coming, um, which will be all the raw data basically that we collect and make available to people to do their own research on. And that's kind of the last thing that would be that make this website ready to go. But if you look under extension, we have data that's coming in from the extension side. We have, and under education, we've developed these language modules for educational development. And you can basically look at any of these and go to the modules and actually sort of take a take this as like a online course and do pre and post test analysis. Pre and post test quizzes to give you an idea of how well you do know the content. So have the pre-post quiz, have an outline, and then this is some of the information. So there's 6 of those now. If you go to the dashboard, this is where we are basically on. We're storing our data on Amazon AWS, the Amazon Web Service, and linking our website to that through APIs. So we're collecting a lot of the data through an API from the field that are IoT sensors that goes to AWS, and then AWS, we're pulling data from that and loading it onto our website. So this website here, I try to see where I have my radio coming on. So so this dashboard here at the very top, this is weather data. So this is updated every 15 minutes. And it's just the solar radiation, rainfall, and just basic weather information. But this is from the weather station on the farm. So this picture at the bottom left here, you see this. I'm overlaying here is weather station. So that data is from that weather station. So we're getting data directly from the farm on that. If you look at this picture here, this is, you can select what kind of information you want to see. So this is RGB, which is just a optical image, and then NDVI is the vegetative index, showing the plant vigor at that point. You can go through and look at this sequentially over time. So we take these images once a week, so I can scroll forward on this line here and see what the plants look like from a bigger standpoint. I can click on sensors, and it shows the where our water moisture sensors are, soil moisture sensors. I can click on field and select different fields so that you can see which field we're looking at. On the right side, this is the soil moisture sensors. So later when I'm talking about soil moisture data, it's data that's coming from these soil moisture sensors, and there's multiple sensors in each field. So this is the north pivot. If I go over here, that's that field, north pivot. This is this year, 2025, and these are 4 sensors that are in the field. So when I click on them, the corresponding sensor lights turns yellow over on the other side, so I can pinpoint which sensor I'm looking at. And then this data is basically the higher the value, the drier the soil. And we have a threshold that we've set through testing that triggers an irrigation. So whenever you can see over here, this green line, which is a 16-inch depth sensor, crosses that line, that's telling us that it's time to irrigate. The bad side to that is this basically means you've stressed the plant. The irrigation line tells you when the plant's stressed and needs water. Growing degree days, we can plot that for the different crops. And growing degree days is a good way of assessing your plant development. There's tables from almost all crops on where it should be in its development based on the growing degree days, which is basically if the temperature is above a certain level, the plant is physiologically developing and growing, and we know how many growing degree days it takes for it to reach certain developmental stages, like when it'll start flowering, when it'll start creating fruit, when it's time to harvest. So we've been trying to, we can also check rainfall. And then one thing with our air temperature is, you see here, these bars are the max, min, and average for this year, and the blue in the background is historic data, but we only got 1 year data, so that's last year. So you can basically, looking at that, you can see in this time period here, like August 28th to 1st of September, the average temperature this year was much lower than last year. So it gives you a good way of assessing, comparing things. You can also look at it over different time periods. We haven't had rain here. So if we look at this rain here, our last rain event, which is this one here, was August 30th. And even you can look over the last couple of, about a month almost, we haven't had that much rain. So it's pretty dry now. So this is just kind of a visualization, the dashboard, for people to see different parts of the data, and it's automatically, though, updated with these APIs automatically pulling data as it gets pulled into the AWS and then extracted. What we're going to do again later is take this information and the raw data and put it in our data explorer. And yeah, so update. So just to let you know, if you want to see updates, we do updates every 2 weeks. And so we do a research update and then a data farm update. So the research update is updates on research we're conducting, which is kind of what I'll be talking about today. And then the data farm updates is really showing the operations on the farm, like when we planted, when we harvest, what the weather's like. Let me just pull one up. So this is July. So we do there's a farm update every month, and there's a research update every month. But this just kind of gives you at a glance what's going on with the farm. And so we do those every month, and then the research updates will just depend on what kind of research that we're looking at. This latest one is actually what we're talking about tonight, is our database evaluation, where we're looking at different databases for our data management. So with that, go back to this. Okay. So all this information, again, we're trying to develop some kind of a management assistant for the farmer, so that we can take that information and use it for making decisions. So that's one of the challenges, and I think I've shown this maybe in my last presentation, but when we're looking at all this data we're collecting, you have UAV or drone imagery or satellite imagery. We haven't utilized satellite imagery yet, but drone imagery, high spatial resolution, 2 or 3 centimeter per pixel resolution, but low temporal resolution. We take it once a week. Then we also have the sensors on the ground, like the soil moisture sensors that I was showing on that graph. High temporal resolution, we're collecting data there either once an hour or once every 15 minutes, depending on the values that we're collecting. But it's very low spatial resolution. We only have 4 of those in a 10-acre field. So very disparate time frames, resolutions. So you try to fit those together best you can. So looking at data collection, I kind of break it up into 4 different things. One is operations data, which is kind of like when did we plant, how many seed per acre did we put out, what was the emergence. It's kind of how much time did we spend driving the tractor, how much fuel did we use. We're collecting all that information because what we want in the end is not just demonstrate some of these practices, but also demonstrate whether it was economically relevant or good. Did you make money? Did you improve your farming practices because of it? Because as a demonstration farm, we're bringing farmers out and giving them presentations on these different practices. IoT data, which is right now primarily it's the soil moisture sensors and the weather station. So those basically relay information to a cellular modem that transmits it wirelessly to the internet, where we collect that information and store on the Amazon Web Service. We also have a pest monitoring system that we're developing, and we're doing that as well, but we haven't. I'm not going to talk about that tonight. It's still kind of in development. Then we have our aerial data, which is the UAV information. That's not connected directly to the internet. Right now we're manually taking that data off of the UAV from a data storage card, micro card, and then manually processing it into stitching it together, creating the RGB image, creating the vegetative indices images, and then downloading those onto the Amazon Web Service. We've automated some of those processes, but that's time consuming right now. And then we just have manually collected data. So a lot of that's like you have to manually go out and collect a soil sample, send it to the lab, get your lab results back, and record what your soil sampling looked like. And that data is then used to prescribe the application of like nitrogen, phosphorus, potassium. Lime is really important because it adjusts the pH of the soil, which allows the soil to utilize nutrients if it's in the right pH range. Scouting, that's mainly looking for pests that you might need to apply a pesticide to. But a lot of things now are still manually collected. The scouting information is for like pests. We hope to take some of the load off of manually doing that with our IoT pest monitoring system. On the right here, this is a software that actually we store information on in kind of interim before we translate it for the Amazon Web Service. It's kind of interesting because it's still used today. It's one of the most popular ones, and it's been around. It was around when I started over 25 years ago, and it looks almost identical. It has not changed its graphical user interface in that whole time. So it's kind of interesting. There are a lot of people working on these types of things, of like database storage and management, which is something that again we're working on, but it's very out of not very modern looking. So I kind of mentioned this, and I'll kind of go through it quickly, but like the fuel usage, time it takes to do operations, how much it costs, or what our input rates for, say, fertilizers, what our seeding rates are for the seed we're planting, Again, pesticides. I'm sorry, all the costs associated with that. We're monitoring so that we have a good economic analysis of what's happening. And then the IoT data. So I mentioned the soil moisture sensors. This is the company that we're using that we bought the soil moisture sensors from. These long poles here are what goes in the soil. And in our case, we have soil moisture sensors that go down 24 inches into the ground. And we have 3 sensors, one at 8 inches, one at 16, and one at 24. That's so that we can monitor the moisture at different levels of where the root zones are. So early on, the 8 inch is important for the younger plants, but as the plants grow, the roots go deeper into the soil, and we want to track the soil moisture closer to the root zone. So we actually have 3 levels. We have the weather station, and again, that information is all relayed to the internet. One thing we're also monitoring, besides I talked about insects with our pests, with our IoT pest monitoring system, we also have cameras out on the farm that's now tracking vertebrate pests, which has become, for cotton, the #1 issue pest-wise is deer. Deer come in and chew the plants off early in the season and have a significant effect. So we're starting to actually track that and ways of curtailing pests, those types of pests. We're also integrating livestock onto the farm this coming winter, and we've put also, this is a deer. So this is actually a picture from the deer camera that's on the field. So this is a doe, a female deer. She's actually just outside our peanut field. So we have peanuts and cotton this year. So the deer like peanuts a lot as well, but they'll dig the peanuts up. The peanuts grow in the ground, and they'll eat the peanut pods. But we've gotten into a really interesting project on that because what their nutrient needs vary depending on when they have does. I mean, when they have their fawns, and then the bucks are there as well. So we're looking at that. This is cattle that will be moved onto our farm this winter, and the thing around their neck is a GPS tracker. So we can track the location of all the cattle, and also it creates what's called a virtual fence. So the GPS, you have a software package, and you can mark the boundaries where you don't want the cows to cross. And when they get close to it or start crossing it, at first it starts making a audible sound, and then it gives a little shock. It's not very powerful, and if they keep going, it stops. But if they do go in, they'll normally just turn around, and they learn that pretty quickly to avoid that shock by just when they hear the beep, they know that the shock will come if they kept going, so they'll back off. And so that allows us to actually move the cattle around on the farm to forage where we want them to without creating a physical fence. We can just, through software, move the cattle where we want. And one of the reasons we're doing that is so that they get the optimal forage usage, but also because they then spread their waste around the field, which then kind of goes back into the field as fertilizer. Our aerial data system, we're actually using 2 drones. One we manually fly. It has a multispectral camera, which means this one has 5 basically lenses on it, and each one filters out all wavelengths except one wavelength, or a range of wavelengths, a narrow band. So you can record an image that just shows the red reflectance, the green reflectance, blue reflectance, near-infrared reflectance, and what's called the red edge. And those last 2 are very help indicate plant health through some physical changes in the plant. Red is also very important because red is the color of chlorophyll absorption. So if you have a good dip, if you're looking at the reflection curve, you should see a dip in the red, which means it's absorbing the red light, which means it's producing chlorophyll. So a healthy relationship between red near infrared or red edge tells you a lot about the health plant. We also have a drone docking station, which is to automate the system. So one of the downsides to drones is you have to be out there and set it up and run it and be there all the time. The drone docking station that's shown here, you can automate its takeoff and mission, which is it going back and forth collecting the images. So it's got a thermal camera on it. So we can't really interchange them. We have to use them for different reasons because they have different cameras on them. But thermal imagery is something that we have that can be used for the animal identification, and also thermal is a good indicator for water stress in a plant. So when a plant starts losing too much water, it actually closes its pores, its stomata, to conserve water. But kind of like a person who's not sweating, it heats up then, and that heat signature tells you that you have a water stress plant. So this kind of gives, this is like a table of some of this data. I was talking about like the operational data. We're trying to take that data and turn it into information for the farmers on what the cost is of some of these things. So I'm not going to go into a lot of the details, but it's basically the amount of water that we use, the amount of fuel that we use, the cost of planting, scouting, harvesting. So we just kind of use it to keep up with all the costs. The end goal is to create what's called an enterprise budget, and an enterprise budget already exists for individual crops, which tells you like you can estimate the cost per acre to grow peanuts and cotton. What we want to do is have a precision agricultural budget that kind of gives a farmer an estimate of like, if I do these things, this is how much it'll cost on the farm. So one of the things that's also kind of an issue, and this is a picture of a cab. What you end up with sometimes is you have a tractor that's a John Deere. That's the popular tractor, but you're pulling an implement behind it from another company. You have maybe a GPS or global positioning system from a third company. And then you may have other companies associated with other pieces of equipment that all have their own system. So this case here, you're not using all these monitors at the same time, but they're all maybe indicative of different pieces of equipment you're using. And they all have different formats for their data storage, and just different ways of working with them. So it can be really daunting for farmers, as you can imagine, to be dealing with this. And if you watch the YouTube videos on this, you'll see farmers really frustrated. And what's happening is the farmers will get the system set up by the technician from the company that sells it to them. They set it up for them, and they won't touch it after that. So they don't really utilize anything other than what it's set up. Just the picture that they get is pretty much what they use. So, but like John Deere has JD Link, that's their software platform. Ag Leader has Agfinity. Then you have things where you just have to have the data manually downloaded. Most systems do have something that it's collecting that data and storing it, but So as you can imagine, they all have their own data formats. So that's some of the challenges of combining all this information together beyond just the heterogeneity of spatial and temporal dynamics is also the companies you're trying to collect the data from. So I mentioned the IoT. I've already shown you the dashboard. That's the IoT data is something I think that we're going to go to more and more of just trying to automate that data transference to the internet straight from the field. But there's still some issues with doing that, especially the aerial data. I just showed this for irrigation scheduling. So I mentioned that we have a threshold for irrigation, and what we'd like to do is actually make that, with this dashboard and with the information we're collecting, we can alert the farmer to say, okay, you've crossed the threshold, you need to start irrigating. And that threshold is going to depend on the crop, the depth of the roots, what your days after planting or the vegetative state of the plant. But you really like to predict when to irrigate before there's a stress. And even if you, let's say, even now, when we say, okay, it's time to start irrigating, the center pivot is very slow as it goes around. And to make one full circle, it takes probably, for our system, it takes over a day, more than 24 hours. So your plants don't even get, some of them are going to wait a lot longer to get watered and even get more stressed before it gets around to watering them. So one thing we're looking at is forecasting the irrigation need, and to do that, we're modeling the soil moisture prediction, or predicting what the soil moisture is going to be using data that we've already collected for that field. So another thing I haven't talked about much, well, I'll talk about it a little here now, is when we're creating these models right now to say forecast when to irrigate or forecast when to add nitrogen or forecast anything. The way we're looking at it is these forecasts are developed around a certain nomenclature or certain approach, whether it's like using LSTM forecasting series model or whatever, but it's continually updating and tuning itself to the farm that you're on. So it becomes, on a yearly basis, it should improve itself as it collects more data and trains itself up. So that model is not going to be transferable to another farmer, but the base model of that farmer could use on his farm and adopt it, and it start working. But each model then would start being different in its predictions and its recommendations. So we're collecting soil moisture data and weather data primarily to create a data set. This is just showing the data set that we created to extract features using LSTM that we then feed into a predicting model, in this case XGBoost, and predict what the water level or what the soil moisture is going to be over the next, say, 7 days, so that you can see, based on that prediction and the weather forecast, whether or not you should plan to irrigate or not. So this is just some actual soil moisture. So taking like the picture I showed that was that's on the dashboard, this is just looking at a 168-hour section of that and predicting, or taking the actual soil moisture and several months of previous data and creating a predictive model of what the soil moisture should be starting, to say today, what's the next 7 days going to look like. So it's trained basically using historical or series of soil moisture data, air soil temperature data, and the precipitation. And the goal of this, and we're pretty close to this right now, is if you look at this over here, this is our data. So let's say we have this field, it's the South Pivot field. It's got cotton and the threshold is 45 kilopascals. So soil moisture can be measured a couple of different ways. One is the actually pressure it takes, or the vacuum it takes to pull water out of the soil. And that's the most accurate. It's more accurate than volumetric, which is the amount of water in the soil, because it takes into account whether the soil is very, if it's sandy or if it has a lot of clay, which there's a big difference in how well the roots can pull water out of each of those. But anyway, we have all this data from each of these sensors, different depths. We create a weighted average of all that based on some previous research, and pull that together with the historical soil moisture data and historical weather data to come up with our LSTM soil moisture prediction model. And then we take our weather forecast with that and come up with a irrigation decision. And my student right now is looking at how to create these like an agent to work with LLM that would be proactive for the farmer. So the farmer doesn't have to continually like check his phone to see, today, should I irrigate tomorrow? The phone or the large language model would alert the farmer to what the status is and what his, plans he should be looking at in the next week or so, so that he can be aware of it and not, accidentally miss something. There's so much information. Even without computers and everything, farmers are juggling a lot of information. But the idea behind the large language model and the agents is to make sure that they get all the information they need to make the decisions without missing anything. So another system that be very similar is plant growth regulation. Plant growth regulators help to optimize fruit development, regulate plant maturity, reduce chance of lodging. So it's kind of like you apply the nutrients to the plant and then you watch it. And with the nutrients, and you don't really have control of the weather, if it rains a certain amount, over a certain period of time, it may cause the plant to grow too fast. And then your main stem may get too spindly and it falls over because it extended too fast, too long, and that's lodging. Basically, lodging is the plant falling over. Also, fruit, you want, for harvesting, you want it more in a compact plant. You don't want it spread out a lot. You lose a lot of the fruit that way, either falling off or through the weather. So anyway, the plant growth regulator is really important, and not just for cotton. It's used in a lot of crops for this. It's the use of it and how it's employed now. It kind of depends on the growing degree days I mentioned before, or just the plant development. It's estimated by going out in the field. For cotton, it's going out in the field, and you see this picture on the right is a ruler. You look at the main stem, and each stem coming off of the main stem is called a node. And so from the top, if you count down to the fourth node and then the fifth node, the distance between those two should be less than 2 inches. And so if it's growing too fast and it's elongated, so that's called the elongated internode length, then you need to add plant growth regulator to prevent that from happening. So there's two ways of doing that. Two measurements that are made for that. One is this internode length. The other is the ratio of the height of the plant to the total number of nodes, and that's the height to node ratio. So these are all manually made in the field. They go out with a ruler, measure the height or measure that distance. And as you can see, that's a spot measurement. So it could vary widely across the field, but you're going to make your decision based on just whatever little samples of data that you can do manually. So we're going to try to use drone data to do all that. and that way we get a good view of the whole field. We can estimate whether or not PGR needs to be used in part of the field, none of the field, or at what date to do it. We're using the RGB image. We're going to look at vegetative index, and then also like rate of change, like week to week. We take a weekly aerial image, week to week, what's the growth height difference. So this aerial image here is early on. These top two fields here, we didn't have very good emergence. You can see that there's a lot of empty spots, but I'm going to go through this. So this is the data as we look at it over each week. So you can see the plants get larger as the weeks go by. This bottom field is peanuts, so it actually did really well. The problem we had when we planted this, so we just didn't replant because we didn't need to. A farmer would replant this, but it's one of those farming things. We had a date that we had to plant, and it started raining, and we went ahead and planted as it was raining, and so that messed up the planting a little bit. So anyway, that's one of those things that we're looking at. And so this is just actual data for the internode length. And this dotted line, that's the threshold for when you would want to add PGR. And about 52 days after planting is when it jumped over 2 inches. So you'd really want to apply before that to prevent it from ever reaching this level. These are all weekly data. So every week the data was collected. And then this is the height to node ratio. Again, the x-axis is the days of after planting, and then the height to node ratio. So in this case, if you use 1.5, that would be very similar to the internode length. But if you use 2, which is actually also another recommendation, it would be much later, or you may not even apply plant growth regulator based on that recommendation. So they probably need to do some testing in your own field to see if which one was best. But the whole goal of this and talking about it is I want to use a drone and make some measurements to predict what those values are. So one is height. We know that's a very significant value that we have to estimate. So this is just a table of different UAV metrics that were used to estimate the height. We manually measured the height, and then we estimated with the drone, and just seeing which metric to choose from that would give us the best value. And this last one is the best. I can't remember the difference in all these, but they're all using a digital surface model from the aerial image, which is kind of showing the height of the plants, and then a digital elevation model, which is the ground, and figuring out what the difference of that is. So this is so we just chose this. This is our way of estimating the height. And our goal then is to estimate the height to node ratio, or the internode length, using a function of the height estimate, the growth rate, which again is that difference between days, weeks of the planting growth. So how much did it grow from week 2 to week 1, which, as you can imagine, has to have some kind of correlation to the extension of the internode. And then the vegetative index, which is indicating what the growth vigor is. So it kind of may have some actual collinearity with that. And then using some different testing out. Right now, my students looking at some different algorithms for estimating what that should be. So if we can we can estimate what that is. Again, we can decide, we can predict what the internode length is going to be, or when it might cross the threshold, and then preemptively apply the plant growth regulators so that we don't enter a location where it does extend above 2 inches, or whatever that threshold is. The plan for the plant growth regulation application in advance to optimize, and maximize things, as we've mentioned before. I'll briefly talk about, we're looking at different databases, and basically we're looking at a document database, which would be like Mongo database. We're looking at graph database using Neo4j, and really the things that we're looking at right now is that we can do the same types of analysis and that sort of thing with each one, but we're kind of looking at performance from a standpoint of if there were a lot of users or a lot of data going back and forth, which one is the most efficient use of resources. So these are some just metrics that were tested on that, like CPU utilization, memory utilization, response time of the database, just so we get, like if all things being equal, from an analysis standpoint, which won't be the best from a efficiency of a resource type thing. So we're also going to add a vector database to this, I think, to do some testing. So, basically, to summarize this, there are data collection barriers. You have multiple data types, spatial scales. There's manual measurements need to be made. Data that we collect from the manufacturers of like equipment manufacturers off the tractor or the implements all still like to use their own proprietary data schemes. We need to, but the goal of all this is to say take our data and turn it into information, and that information be used to do an action. When do we irrigate? When do we add a plant growth regulator? How does that affect our output? So we're doing this in different pieces, but in the end, we're going to put them all together in the sense of like, how does this affect the yield and improve our bottom line? So the yield would be kind of like the overall arching model, and you have all these different pieces that go to that we can adjust in season to modify that as we go through it. So the end is a decision assistant tool that is proactive in the way that it can alert the farmer to what's happening on the farm, and they can make the decisions as they go through. So I think that's pretty much everything.
Yes, thank you, Glenn, for this very comprehensive and quite active research you are doing. And we have seen some of this before, but today is the first time I saw everything together. So it's a very nice, talk. So I'll open the floor for questions. We have a few minutes to ask questions if anyone has. You can raise your hand or.
Glenn, can you stop, Glenn, do you want to just stop sharing as well? So then I can.
Oh, sure.
Yeah. So there's one, Harrison.
Yeah. Am I audible?
Yeah, Harrison. Yeah. Thank you. Please ask.
Yeah. Thanks, Glenn, for the insightful talk. Lots of interesting ideas. So I'm really interested in the image used on the cover page of the talk, like the one showing the drones collecting data to make an informed decision. And I've seen that we've conducted like studies using the drones, like to understand plant stress and other factors. But what I'm really keen on, Kamla, I know is like, have you considered doing something similar for like disease detection? For instance, analyzing each plant individually to see whether it is infected or healthy, rather than monitoring the whole farm.
Yeah, that's I think that's something that could be really important as well. We haven't delved into that too much, but we can definitely do that with drones. One thing that we grow peanuts, and peanuts have a lot of fungicide application. They have a problem called leaf spot, and but the timing of that is important. So yeah, we could use drones for disease detection as well. The thing you have to to think about is to whenever you see the drone information, and you can use like a vegetative index to say, okay, well, this area of the field is stressed. The drones definitely narrow things down, but you still would have to go out and identify, not necessarily every time, but for a lot of times you still have to go out and identify if that stress was a disease, if it was water, was it an insect. Lots of times you kind of know, like if you've grown crops on that field for a few years and you see an aerial image and identify stressed areas, it's almost not always, but a lot of times it's the same stress in the same part of the field. You see it, you get the same types of things happening over and over. So, but drones definitely will allow you to do things, look at a larger area and make better, more precise decisions.
Thanks for that.